Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we introduce the idea of conjugate prior distributions. They are prior distributions that are convenient from a computational perspective. This will be done for the case where the likelihood of our sample is modeled with a binomial distribution and the parameter of interest is its probability of success. Let's begin. Okay, so the main idea behind the choice of a conjugate prior is this. Choose the prior from a family of distributions that has the same functional form as your likelihood. So, as we said at the beginning of our video, we will be discussing the case where our likelihood is modeled by a binomial distribution, which looks something like this, right? So, likelihood in our particular case, and remember we think about that as conditional probability, right? So we have the probability of observing a particular value of our data, right, of a random variable, given a particular value of our parameter of interest, right, which is pi, a proportion. Okay, so our likelihood is going to be binomial, and we know that the probability mass function looks like this. N choose y, which is the same as n factorial divided by y factorial times n minus y factorial. And then what we have is pi to the power y 1 minus pi to the power n minus y. Okay, and we know that the values of y could be y equals 0 or 1 or 2, so on up to n. Okay, so if we ignore the constant, right, ignoring the constant, our likelihood is proportional to just this. Okay, I'm going to be ignoring that constant, and I'm going to be just paying attention to the part of the probability mass function that contains the parameter of interest, pi, right? Let me just mention that here. Our parameter of interest is pi, a proportion. Okay. So, take a close look at this, right? You have seen that kind of functional form before, right? You have seen statisticians would call it a kernel, right? That functional form up to a constant, right? And well, that looks like the kernel, okay, of a beta random variable. Okay, and let me remind you what the probability density function of a beta looks like. PDF of beta with parameters alpha and beta. So let me use f of x, that notation, right? Then we're going to use a different notation, but just the kind of notation that we use in sta360. So we know that it's going to be the gamma function evaluated at alpha plus beta, our parameters. Then we divide by the gamma function evaluated at alpha times the gamma function evaluated at beta. And then we have the argument of our function to the power alpha minus 1. Oops, not what I want. There we are. Alpha minus 1 times 1 minus x to the power beta minus 1. Okay, and we know that the support of this guy is just the 0, 1 interval. Okay. Okay, there we are. So, after seeing the probability density function of a beta, we think that it's a good idea that a good candidate for a prior, a conjugate prior for pi is the beta distribution family. Okay, so let's say that. Let's use as our prior, and let me just say this, our conjugate prior, and we will be using the notation p of pi, right? Well, this guy is going to look something like this. That's going to be our proposal. Now let me change this guy here. Going to have pi instead. There we are. So let's do the math, right? Because if we chose our candidate wisely, the posterior distribution will belong to the same family of distributions as the prior. So if after we do the math, right, we are proposing this, a beta distribution as our conjugate prior. So if after we do the math we realize that the posterior distribution has a beta distribution, then we were right. We chose wisely. Okay? So let's do the math. Let's find the posterior. Let's find the posterior distribution. Okay, so let me remind you what the posterior distribution looks like. So our notation is going to be p of pi given y, given our data, given our sample, right? So just, using the definition of a conditional probability, we can rewrite that conditional as joint divided by marginal, right? And this guy the numerator, that joint, we can rewrite in terms of the main ingredients in Bayesian statistics. So it's going to be the product of our likelihood and our prior, right? So prior times likelihood. Let me copy paste this guy. This is our likelihood. And we're going to be multiplying by that prior. So prior times likelihood. That's our first candidate, right? There. So we can see what we have there. Okay. So now the denominator, right, is going to be, as we said before, I just got rid of that, the marginal, right? So to find the marginal of y, what we have to do is integrate the joint with respect to pi. Remember? We've done that before. So it's going to be the integral from 0 to 1 of our joint with respect to pi. Okay? Make sense? Got it? Okay. So, numerator, no problem, right? That's going to be easy, but let's try and make it look a bit nicer. Okay, let's do a little bit of algebra. So here we have pi to the power y, right? So how about we combine these terms, right? And the other term that I would like to combine is 1 minus pi, right? Okay, so let me move this one here. And then instead of y, we are going to have y plus alpha, or alpha plus y, either way. Minus 1. Okay, now this one, it's going to be n plus beta minus y minus 1. So let me copy this guy, both of them. N plus beta minus y minus 1, right? Now we don't need these guys anymore. Okay, so we just did a little bit of algebra. We combined these terms, we just had to add the exponents. Make sense? Okay, so now that was the numerator. That wasn't too bad. Let's talk about the denominator. Okay? Let's find that integral that we have there. Okay. So, first step, let's use the linearity of integrals, right? Note that, well, not the linearity, the fact that what we have here is a constant with respect to pi. Okay, since we're integrating with respect to pi, we are going to have that these guys could be outside that integral, right? So let's do that. Let me place these guys here outside our integral. Okay. Now let's do something similar to what we did before, right? And I can borrow that from the numerator. Or, well, I might as well do just this, right? This is exactly the same thing that we did for the numerator. We're just combining these terms, okay? So I don't need this guy anymore, and now let's combine these two. And this is plus. Okay. Then I don't need this one anymore. Okay. So now let me make a little change of variables here. Let me introduce an alpha star. And alpha star is going to be alpha plus y. Okay, so the parameter for the beta from the prior, right, for the prior. And similarly, I'm going to be defining a beta star and this guy will be n plus beta minus y. That's how I'm defining it. Okay? So now what I'm going to be doing next is just rewriting the integrand, right? This guy here, using alpha star and beta star. This guy is beta star. So we would like to find that integral, and we realize that the kernel, right, meaning the functional form except for the constant that would make it a legit PDF, looks like the kernel of a beta distribution. So what we're going to be doing here is, well, we're going to multiply by the constant that would yield a legit beta, right? So what we need here is gamma. Let me copy this entirely, and then I'm just going to modify that. Okay, so instead of alpha, we need alpha star, right? Instead of beta, beta star. And we divide by gamma, evaluate the gamma function evaluated at alpha star times the gamma function evaluated at beta star, right? And that's a constant, but we are multiplying by that guy. So if we divide by the same quantity, we're just multiplying by a1. Okay, so here we are going to have the reciprocal of that quantity that we needed to make this guy here the PDF of a beta. And then, since we are integrating a beta with parameters alpha star and beta star over its entire support, you know, the region where the PDF is non-zero, in this case from 0 to 1, this is just 1, right? So next line, what we have is just that. The integral is just 1. So bottom line, the denominator is going to be this guy here, right? After we did the math, that's our denominator, right? So let me go back to what we had here, to the expression for our posterior, right? This guy is our posterior. Back to our posterior distribution. What we have is this, and let me copy paste the expression, the expression for our posterior, which was this, joint divided by marginal. The numerator wasn't that bad, it was just the product of our prior times our likelihood. The denominator was a bit uglier, was originally that integral, but we did the math and we had this. Okay, now before we simplify that expression for our posterior distribution, an observation. This guy, this nasty looking guy, our denominator, it looks ugly, but it is just a constant. Yeah, an ugly looking constant, but a constant still. Okay, so now, as I said, let's try and simplify that expression. So note that we are multiplying by this guy and dividing by the same guy, so they cancel out. We have gamma evaluated at alpha plus beta divided by gamma evaluated at alpha times gamma evaluated at beta. We have the same constant here, so these guys also cancel out. Okay, so in the end, right, what we have is something that is nicer. Just that, right? Now let's simplify a bit more that expression. Note that we are dividing by gamma evaluated at alpha star plus beta star, right? Here. So that would be the same, that's equivalent. We could rewrite that expression like this, just doing a little bit of algebra. This is the same as this guy that multiplies the numerator, right? And this guy is dividing, so let me put it with this guy here, okay, as a fraction. Okay, makes sense? Oh, let me just copy that guy. Then I'm going to get rid of that thing. I don't need it anymore. So After simplifying a bit more, we realize that our posterior distribution looks something like this. Okay? And that expression is valid for pi between 0 and 1. And when we take a good look at it, we go, guess what? The posterior is a beta random variable with parameters alpha star and beta star, right? So posterior distribution is beta with parameters alpha star and alpha star happens to be alpha plus y, right? And beta star is just, you know, n plus beta minus y. Remember? Because that's how we define them here. When we did the math here for the denominator, right? So that was alpha star, beta star. Make sense? Yeah? Okay, so we could write it down like that just to make it look nicer here. Right? Okay, so our prior and our posterior belong to the same family of distributions. Therefore, a beta distribution is the conjugate prior for a binomial likelihood when the parameter of interest is pi. Make sense? Okay. Now, let me just make a comment about proportionality. Okay, that is going to be useful. So, let me open a new one here. So, proportionality. Well, when two functions differ only by a constant, they are said to be proportional to each other. Okay? Now, there's a symbol that looks like an alpha. Let me see if I can find it. Let me just give me a sec. Okay. So, as I was saying, there's a symbol which looks like an alpha, but it's not an alpha. Okay? This guy here. So, that symbol is read proportional to. So, that symbol is read proportional to. Okay? So, let me use that proportionality symbol to summarize what we did. So we had a prior, right? P of pi, our parameter of interest was a proportion, pi, okay? So our prior was proportional to a beta distribution, okay? So something that looks like this: pi to the power alpha minus 1 times 1 minus pi to the power beta minus 1. Okay, so our prior was a beta. So thanks to that proportionality symbol, I am ignoring that constant that comes along with the PDF of beta, right? So I'm just saying, okay, it's proportional. I know that the PDF looks like this up to a constant, okay? So that was our prior. Now let's talk about our likelihood. Our likelihood was given by a binomial, right? So binomial. And we wrote that down as the probability of observing a particular value for our sample, for our random variable y that reflects the data, given a particular value of our parameter of interest, which is a proportion, right? So that likelihood is going to be proportional, meaning ignoring that constant, to pi to the number of successes that we observed in our sample times n sample size minus number of failures. Okay, well, n minus y represents the number of failures, so n minus the number of successes, we have number of failures, right? Okay, so our likelihood looks like this, right? So posterior. We know that our posterior is a similar conditional probability, but we reverse these guys, right? We want the conditional probability of pi given our data, right? So, and what we know is that what we do is prior times likelihood, which is the joint, divided by the marginal. But what we said, and we did the math step by step really carefully, what we realized is that the denominator is just a constant, a nasty looking constant, but a constant still. So let me just write this down like this, that our posterior is going to be proportional to our prior times our likelihood which means that our posterior is proportional to that product here, right? Prior times likelihood. So what we end up with is just alpha plus y minus 1 right? And then we have n plus beta minus y minus 1, right? right? And again, when we see that, right, we go, oh, let this be alpha star, let this be beta star. So what that means is that our posterior is proportional to a beta distribution with parameters alpha star represents the alpha for our posterior distribution, and alpha star is alpha plus y, and beta star, the beta for the posterior distribution, will be n plus beta minus y. Okay? So this idea of using proportionality, the proportionality symbol, right, it's kind of a shortcut, right? We're saying, okay, up to a constant, this makes sense. And now we realize that, I mean, we did the math here, step by step, right? So we end up with the right distribution and with the right parameters. Okay, so in the future we're going to be using this idea of proportionality more often, okay, as a shortcut. Okay, make sense? So bottom line, the conjugate prior, when you have a binomial likelihood and you're interested in saying something about the parameter pi, the proportion, right? The conjugate prior is a beta, right? And after we did the math, we realized that it is true that the prior and the posterior distributions belong to the same family, which is basically, you know, the definition of a conjugate prior. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.